Welcome to EET3329C Communication Systems at Valencia College for the fall semester of 2020. This is lecture number 5, and this is your lecturer, Dr. Wilfredo Rivas Torres. And today we will be covering digitization. And this is a single part lecture, not like our other lectures where I have been dividing them in different parts. So today our topics we'll talk about the sampling theorem, PCM, which stands for pulse coded modulation, digital multiplexing, and DPCM, which stands for digital pulse coded modulation. So it's quite remarkable. Digital technology comes a long way, and it allows us to digitize our signals for both storage and transmission. So digitization forms actually the foundation for digital communication. So we actually convert the signals first to the digital format so that and then we transmit them. As we mentioned earlier in the course, uh, the conversion of an analog signal into digital is done through a digital to analog converter or an A to D. And it must have a sampling rate that has to be high enough so that the original signal can be reconstructed from these samples with required accuracy. And then on the other side, on the receive side, you would need to have a digital to analog converter. So something takes the digital samples and converts it back to our analog signal so we can recuperate our original message. Uh, the sampling theorem that we're about to discuss is the basis for determining what the proper sampling rate is, right? It plays a huge role in both signal processing, communication theory, and even in analog to digital converter design. So let's go ahead and talk some more about the sampling theorem. So we call it the uniform sampling theorem, states that a signal, G of t, um, which is band limited. So let's start with the topic of a signal that's limited to a certain bandwidth. And what we haven't, I think, formally ever said what a band limited signal, even though we explained it, but mathematically, a band limited signal is equal to 0, okay, is equal to 0 for any frequency greater than B, where B is the bandwidth, okay? Um, and if you have such a signal, it can be reconstructed exactly, and when we say exactly, we mean without any loss of information. So whatever the original signal and whatever information it contained is still there, right? And you can reconstruct it from its discrete time samples if you take them uniformly at a rate f of s or samples per second. So f of s is our sampling, what we call our sampling frequency, right? And the sufficient and necessary condition for that is that f of s has to be greater than 2b, right? In other words, the minimum sampling frequency for perfect reconstruction, this is the absolute minimum, would be fs equal to b, okay? For low-pass signals of a bandwidth b. Okay, so let's start off by we're going to talk about this example, this figure 5.1 a little bit here. So let's say we have a signal G of t. This is G of t. I know it looks sinusoidal, but it really isn't. So don't think it's sinusoidal. And we're just looking at a portion of a signal, not at a period of the signal, okay? And let's say that this signal, whatever it is, has a certain bandwidth, right? So let's say this is the spectrum, what you see here in figure 5.1b, okay? Let's say also that we're going to be sampling G of t at a rate of f of s hertz. So we're going to take this many samples per second, right? Which is what units of hertz are, right? Per second basis. Now, we should find a mathematical way to express this, right? Because every time we do operations on our signals, we always find a way to mathematically express this, right? And you guys will remember the impulse function. And we actually use the sampling property of the impulse function, right, to do some of our Fourier transforms and simplify some of those integrals that we were doing, right? But it has a real use when it comes to sampling, right? So let's say we have an impulse train, right? Some people will call this a cone because it kind of resembles a cone, but it's what you see in figure part C here, right? So you let's say that these all these impulses, right, repeat periodically every TS seconds, where TS is the period, or 1 over Fs is the sampling period, right? Um, Now let's say that our sampling period is going to generate a sample signal, and we're going to call it G bar of t, or our sample signal, right? And you can see if I take the impulse and uh, I look at where I'm going to be sampling, right? It means that I have a impulse, right? Every TS seconds, and the impulse is going to have an amplitude equal to whatever the signal was at that sampling time. So that means that the nth sample, right? Excuse me, which is located, oops, I didn't mean to do that, which is located at a time t equals uh, nts. So remember, this is the nth sample, has going to have a strength of whatever the signal g of t, g, was at this time period of ns, okay? nts, excuse me, right? Which is the value of g of t. Sorry, there's an f here, but this should have been a t, okay? At t equals n of ts, right? So that's what this function over here is, right there. Okay, so we're going to end up with a whole bunch of impulses, both positive and negative, and those are going to actually be our samples, okay? Now, what is the relationship between the sample signal and the original signal? Well, the sample signal, that's the g bar of t, equals the original signal multiplied by all the impulses at the discrete times ts, right? All the samples, which expressed mathematically, we can express it as a summation, right? And if you express this summation, you'll see that you pretty much get that, right? And notice this is a multiplication. So anything that happens in between the samples is not uh, of our concern at this point. So we only care about what happens at the exact point that we are sampling. Um, Now, our impulse train is periodic, right? And it has a period T of S. It can be expressed as the Fourier series, right? We know all about Fourier series, right? It can be expressed something like this, right? That would be our Fourier series. Therefore, I can actually express our sample signal G as this summation here, which is 1 over Ts. Notice we have to divide by our sampling time, right? And it's just G of T because um, this is our signal, and then we're going to replace our impulse series, right, Fourier series for our impulse train. And then we have this sort of expression. Now, why did we go to the trouble of doing this, right? Uh, we do that because we actually want to generate the Fourier transform of our sampled signal, right? And the Fourier transform would be for our sample signal g of t, d bar of t, right? And we just need to use the frequency shifting property that we learned when we talked about the Fourier transform, right? So our summation actually becomes, right, our sample signal in the frequency domain, or spectrum of our sample frequency, becomes the summation 1 over the sampling period, and the summation of g of f uh, shifted in frequency by n times the sampling frequency. Isn't that a remarkable result? Now, notice where the sampling frequency is, right? So what does that result in? It results in something that looks like this figure E here, okay? And first of all, everything is going to be scaled by 1 over Ts, as you can see here, right, before the summation. And it will be repeating periodically in the frequency domain at a period of, at a frequency of Fs. So notice that this was the original spectrum. Notice that it's still here around DC, but now it repeats itself, right? So you're going to get, we sometimes call these sampling images, right? Because they're an image of the frequency that we want, but because of the sampling process, they were created as the consequence of the sampling process, okay? Um, so our vital question now is, now that we have these samples, can GFT be reconstructed from the sample signal with without any loss of information or distortion? All right, that's what we're after. Or how would we do that if it's possible, right? And obviously, we're having a discussion because it is possible. Um, you can try to do this in the time domain, or you can try to do this in the frequency domain, right? Remember, I said at the beginning of lecture 3 that this is just really looking at the same signal, right, from like a different point of view. Sometimes you look at it from the time domain, sometimes you look at it from the frequency domain. It's where it's most convenient for you, right? So why don't we try to recover it, but let's do it in the frequency domain. So if we want what we call perfect recovery of GFS from the samples, um, it will be possible if there's no overlap among the adjacent replicas, okay? Um, so notice that we have these images, right, of our uh, original spectrum. As long as they're not touching each other, that's what we mean by no overlap. Notice that this spectrum doesn't touch that one or that one. So the replicas don't touch each other. What actually guarantees us that is this condition from the sampling theorem, right? F of S has to be greater than 2 times the bandwidth of the signal, right? And it should be obvious here, right? If you have a certain bandwidth and you go 2 times that, right? Um, then these will not touch each other, because notice that this is the bandwidth. If I go 2 times the bandwidth, that will be over here, right? And it'll guarantee that the image lands uh, separated in such a way from the original signal. All the images end up being separated, right? And if you meet this condition, we can show, and you see the low pass filter here, right, in this figure. This is an ideal brick wall low pass filter. If you see that, if I put a filter right there, I get rid of the images and I can recuperate or get back my original information signal. Okay, and that's what all the sampling theory is about. It's about recuperating your signal, making sure you sample it, and that you separate the images far enough from each other. Okay. Um, so this minimum sampling rate is what we call the Nyquist rate for GFT, and it corresponds to the maximum sampling interval, or 1 over 2 times the bandwidth, which is called the Nyquist interval. Okay. So now you know how to establish the right sampling rate. Now, let's understand this signal reconstruction a little bit more, because we're putting this brick wall filter, right? Now, people will call the process of reconstruction, sometimes people will call it interpolation, right? And it's because when you have the sampled signal, right, you're trying to fill in the blanks, what happens in between the samples, right? That's why people call it interpolation, right? So you have 2 points and you're trying to fill in what comes in between, right? So um, the question is, what is the required low-pass filter, right? And we know that the ideal brick wall filter has this rectangular function that we have studied before, right? And it's has the argument of the rectangular function f over 2b, and we multiply by ts because if you remember the summation, we were dividing by ts. Well, this is a gain factor, right? So we have to somewhere have some kind of a gain factor, right? And if I'm doing this on a computer, like on Octave or MATLAB, it's just multiplying by a number. Okay, is nothing more than that. That's gain. That is the function of gain. Gain is a multiplicative factor. Okay, so this brick wall is what the filter looks like in the frequency domain. But how is it that this filter, which has an impulse response, right? This is the response in the time domain, right? It has this impulse response, which is a sinc function, right? And you can see the sinc function down here, right? H of t is 2bt. Sinc 2 pi b, where b again is the bandwidth t. Let's assume Nyquist sampling, that is 2 times the bandwidth times the sampling period equals 1. You can have just a simple impulse response. Makes our math a little bit simpler, okay? Just getting rid of that factor. Okay. Now, how is it that this works? I'm going to explain it. This is the same thing that's explained in the text here, but um, so imagine that we're going to have a sample coming in. It's going to go through the filter, and this filter, because it's an impulse, it produces the impulse response of the filter, right? Times some factor, right? Let's forget about the factor. It's not important. Without loss of generality, we can do that. But this impulse is going to generate this sinc function, then the other impulse generates another sinc function, and you see that the sinc functions have the amplitude at where the impulse is same amplitude as the impulse, right? And then it has the regular sinc function. The curiosity here is, or what you should take away is, eventually what happens is you have all these sinc functions, and they add up, right? Because we're talking about a linear system, and we apply superposition, right? So we apply superposition of the sinc pulses to generate to generate back GFT, right? From the samples of GFT, we're going to be able to do that, right? Watch. So we know that at the sample point, we get the signal back, right? Because we sampled it there. That's the sample we took. And the next one and the next one, and even the negative ones, right? The ones that are pointing down. Now, what happens in between? In between, you end up adding whatever the sinc functions are. So let's take this point, for example, where they're both here. It seems like the point is going to fall above where our original signal is. But remember, you have to add them, all of them, right? You have to add all of these. Notice that how some of them are negative. So by the time you add all these that happen at this instant in time, the sinc functions, you actually end up with the value of g of t at that point in time. Now, mathematically, the way we represent this is you say that g of t is the summation of your g samples times the impulse response of all these filters that happen right when you get these impulses, right? And we call that sinc of 2 pi b, and they're all going to be delayed by kts. So this is where all these sinc functions are, and this is how we mathematically talk about the reconstruction of the signal through interpolation. Right? Now there's some practical issues, right? Let's say you have a signal that was sampled at the Nyquist rate, right? Fs equal 2b. And you get all these images, right? The repetition of G of S and the frequency. But let's say there's no gap. It's you have it such that your signal bandwidth is B and you're sampling at 2B exactly. Notice that the images actually do touch each other just right there, right? Just as they're becoming zero, that's when the next one starts, right? So we need to pass the sample signal through this ideal low pass filter, which is this dotted line. Now, we have mentioned before that building a brick wall filter is not really realizable in the real world, right? In the real world, because really what it says is, or one of the things that it says is that you need infinite time, right, to be able to do that sync function, which is the impulse response of this brick wall filter. So in reality, what we do is we increase the sample rate and then we create a filter, not necessarily a brick wall filter, but now we allow some kind of a transition region, right? And we sort of approximate this brick wall filter. Now, the reality is that according to Paley and Weiner, right, even this is impossible to accomplish, right? We can increase the sample rate and separate them, but you really can't create a filter that all of a sudden just drops to zero. You just can't do that, right? Um, However, you can continue to increase the sample rate to where you get absolutely very close to even looking like a brick wall filter, right? Um, and to be honest, in the past, right, when our digital technology wasn't as um, versatile as it is today, that could have been a problem. So actually, in in modern technology, if you can't get the signal to images to be separated like this, you just go ahead and increase the sampling rate. That's the quick fix, if you will. Assuming that you can do that, it's not too costly, that you can come up with the right clock signals and everything else that you need to do this, right? And you always try to do it as economical as you can, but making sure that it's still robust, right? It's a robust design, etc. Um, so this is not as much as a problem as it used to be. Um, Now let's have a quick. The book makes a really nice discussion on aliasing, but let me just talk about aliasing sort of from this picture, right? So let's say we have a signal that looks like has a spectrum that looks like this on this figure 5.9a, right? Now let's say that we have a sampling rate such that we would need an ideal reconstruction filter, right? Or we're sampling at fs at fs, which we would produce our filter with a cutoff frequency at fs over 2 because that's what we would quote unquote call the bandwidth of the signal, or the usable bandwidth, if you want to call it that, right? But what happens is, let's say that this is truly the usable bandwidth of our signal, right? These little tails, we don't really care, right? The energy has dropped. Who cares, right? Let's say that. But there's a problem with that, right? As soon as you cut it off, right? What happens is when you're sampling, this tail, if you call it, and the other side of the tail, they actually fold in. Okay. How did they fold in? Well, they fold in because you're using a sampling rate, and notice that they're no longer separated, right? All the images are no longer separated. So this tail is kind of like it folded in. So now when you add and look at the signal, instead of them all being nicely separated like we saw in the prior figure, right? They're not. They actually overlap. And it's this overlap that looks as if the tail has folded back in. Okay, now when you put the reconstruction filter, you're trying to get rid of all these images, and you do, guess what? The part of the tail that folded in does not go away. And now you end up with a spectrum instead of looking like this dotted line, hopefully you guys can see that in the video, right? Instead of looking at this dotted line, it actually looks like the solid line. And any time that either in the frequency domain or the time domain, the spectrum or the time domain signal don't look like the original signal, we conclude we have distortion. Now, a little bit of a segue here. Lab 1, some of my students, you guys did not identify when we added a third harmonic as a distortion. The signal at that point looked more of a squarish signal, and it did not look sinusoidal. That's because the third harmonic was distortion and was making the signal not look sinusoidal any longer. Okay, it was looking more squarish. Okay, all right, let's get back to what we were talking about here. So again, we have this distortion which we did not like. So how do we get rid of these tails, right? The way you get rid of that is you actually put a filter before your sampler. And what do we call this filter? We call this filter an anti-aliasing filter. So it gets rid of anything that we don't want, right? We know it doesn't get rid of it completely. Ideally, it would, right? It would be a brick wall filter as well. And it would get rid of everything that we want. But um, that's not the case. We just want to attenuate the stuff that we don't like sufficiently that even if it falls back onto the spectrum of the signal, or the desired spectrum, should say, it doesn't bother us. It's so low in amplitude and so low energy that at that point, who cares, right? We really don't. Okay. So, and in fact, what happens when you put anti-alias and filter, if you think about it, you actually created this dark signal, and now there's no tail, so all the signals just barely touch each other, right? Okay. Now, in the real world, again, aliasing is not the problem that it used to be, because again, we can increase the sampling rate, right? We have really large sampling rate. Actually, there's some companies out there that have these digital oscilloscopes, and they go 100 of gigahertz, right? So you can only imagine what their analog to digital converter sampling rates are, right? We already say it has to be at least twice that, right? So yes, sampling can be not as much an issue as it was before, except that we continue to increase our data rates and stuff. So we still have to worry about aliasing as we increase our data rates of our signals, right? But that's another separate topic, a little bit beyond of what we want to talk here. Now, even if you increase the sampling rate, we still put in an anti-aliasing filter. And you say, but why? We already increased the sampling rate. We won't have aliasing. Why do we care about the putting an anti-aliasing filter? Well, that's because you still have interference. So these images, right, they fold back in, right? The tails fold back in. But also, if you have some kind of interferer out here, that it itself can have a tail or some component that falls once you sample it along with your signal that falls into the band of our desired spectrum, right? And how do you get rid of that once it falls inside your desired spectrum? The answer is you can't, or you cannot, right? So what we do is we try to filter it before it becomes a problem, right? So we want to take those interferers that hopefully fall outside of our band of interest, and we want to lower them, okay? So that they'll end up not causing us trouble, right? And if you would believe it, even with all the technology and the stuff that we have today, 60 hertz, which is what your AC power runs to, can still be a problem. Okay. All right. So we're going to go ahead and move on from uh, sampling. We're going to start getting into this pulse modulation thing. But the book does a really nice job. Our textbook does a really nice job sort of bridging the two concepts. I like that. Um, So the sampling theorem, right, allows us to represent and store a continuous time signal by and represent it by a sequence of numbers, right? That's what it is. That's what we do when we do it in Octave or MATLAB. We just have a sequence of numbers, right? So processing this continuous time signal is for equivalent to a discrete sequence of numbers, right? Field communication, transmission of continuous time messages is really what we do is we do this transformation to a sequence of numbers, hopefully binary numbers. That's why we call it digital, okay? So this relationship leads to a new technique, right? Where we can take all these continuous time signals and transmit actually pulse trains, okay? Once the continuous time signal t is sampled, the resulting sample values can modulate. Now here we're using the term modulate. Um, you probably are used to thinking about modulation as I need a carrier. I'm going to change one of the properties of my carrier, sinusoidal carrier, which is the amplitude, the frequency, or the phase, right? You can have other kinds of carriers, right? In this case, the pulse can be a carrier. Remember, it's like your postal carrier, right? It's something that carries information, and a pulse can do that, right? A simple pulse just like this can actually carry information, right? And how can it carry information? Well, it can carry information in amplitudes, like in B, right? You just have a pulse which has a certain amplitude. It still has a width, but it has a certain amplitude, right? Actually, you can carry information in the width. So the higher the amplitude of the signal, the wider the pulse, right? Or you can actually say, okay, I have a certain interval. Depending on where inside that interval the pulse falls, right, or the position within that interval, that is proportional to the magnitude of my signal. Notice this pulse happened fairly late, right? No, a little bit earlier, a little bit earlier. Let's say that the dotted line is where the pulse would have normally fallen, right? And then again, it falls back, and then you can see it falls a little bit later, and then so earlier means positive, and the earlier, the higher the magnitude, right? If you go all the way to the top, and the later it falls, the more negative the value of the continuous waveform is, and therefore the more time it took for me to the position of the pulse is delayed in respect to what a nominal value would have been. And we can measure this difference and we can reconstruct our signal that way. So everything is proportional. Um, this forms the basis of postcode modulation, right? And more on this to come. So talking about postcode modulation, here's a block diagram of what that means. So we start off with some filter, and the author calls it a low pass filter, right? We put a low pass filter. It could have been a band pass if that was what made sense. Here's where we sample. Oh, here's our sampler. Here's where we applied the sampling theorem, right? We want to sample at Nyquist rate or higher. Um, and then you need a quantizer. We'll talk about what a quantizer is. But we sort of mentioned this in the very first lecture, right? When we talked about um, digital signals and the like, we said that they only can take discrete levels. So you have a continuous signal, but then there's a discrete signal. That's what the quantizer is going to do for us. And then we convert that to digital with some bit encoder. Okay. Um, an analog signal. Okay, I think I already mentioned everything that's in the text here. So let me not read that again. Um, so what are some of the advantages of doing this, right? Because, all right, so we created bits and fantastic, right? But why, right? So we're always in this unsatiable desire for more and more bandwidth, more and more data, right? The faster we can get it and the more we can get it to the more people we can get it, the better, right? And then different people want to, not everybody wants the same information right now, but everybody wants to have the same conversation. right? Sure, if you go to like a course like ours, everybody has to listen to the same thing, right? So we're transmitting the same information to a group of folks. But if there's another course, well, those folks are receiving a totally different kind of information, right? So one of the advantages of pulse modulation is that they permit the simultaneous transmission of several signals and what we will call time sharing, right? And this time sharing, the technical term is called time division multiplexing. Now, we did study frequency division multiplexing. Remember that? That created different channels, like on our radio and our televisions, right? And the same concept applies to phones, cell phones. And this time division actually applies to modern digital cell phones. What it is you're going to share the time. So think about a pulse has a finite duration, right? So it only really occupies a fraction of the time, and the rest of the time is idle. There's nothing happening. So we can actually interweave different signals, right? Um, and I think I missed something. I forgot to mention this. I'm sorry that I'm backtracking myself. So, by the way, when we talk about the amplitude, we call that pulse amplitude modulation or PAM. P, PWM is pulse width modulation when we change the width, and pulse position is the one where we change the position. Sorry, I forgot to mention that. So, and what reminded me is, let's say we have two PAM signals, okay? So this is the one where we change the amplitude, right, of our pulses. Notice that the light gray is one message, and the dark gray is the other message. So we have a G1 and a G2. Notice that they're going through the same channel, and they're sharing. Let's say it has to go to some certain FM channel. They can share the same frequency, but they happen at different instants of time. Okay. Um, so in a real sense, TDM and FDM are the dual of each other, which is sharing the same channel. Okay. Okay. Quantization. We started talking about. We mentioned it, but what is it? Well, quantization, what it is takes your signal, and this is the um, component which is called a quantizer. Is going to create this quantization level. So it takes your signal and it divides it in L levels or sub intervals, as our book sometimes referred to it. I like to call them quantization levels. So let's say, like in the figure, we have 16. Notice that if your signal falls anywhere inside one of these intervals, your sample is going to be converted to the midpoint, right? So if this was the signal can take anywhere from 0 to 16, well, you would get one of the values, right? And converting from digital, right? If you fall in this interval, it will convert it to 0, right? Converting this digital number back to decimals, it will convert any sample that falls in this interval to 1, 2, 3, and so on. Okay, doesn't matter if you fall, let's say this is number 3, if you fall anywhere between 2, uh, 1, 2, 3, within 3 or 4, right? It assigns the value 3 to it, right? Somewhere in the middle. Well, I actually did that wrong, but you guys hopefully get the idea. Um, so in order for us to digitize the signal, we need the quantized samples, and they will take on any of the L values, and this all happens in our analog to digital conversion process, by the way. Sometimes they call this the L array. Oh, I don't know how that V got into there, but this should have been a Y, L array. Oh, I couldn't do that, sorry. Um, all right, so it's an L array system. All right, so we then take these levels and we convert it to binary, what is known as a natural binary code, right? So if you look closely, the positive side, they went 0, 1, 2, 3, and normal digital. How do we express a negative number in binary? Well, no, there's different codes, but in this one, we actually put a 1 in front of it. And then if you go down and you think of the first one as the negative, or the first bit as the either positive or negative. Positive, we use 0. Negative, we use 1. You'll see this is 0, 1, 2, 3, 4, 5, 6, 7, 8, negative, right? So positive and negative. We call this a natural binary code. And this is how we take, and hopefully by now, this is you guys see how this is how we take our original signal, message signal, MFT, and we convert it to a digital or binary signal. Okay. Um, so the signal a little while ago when we were looking at this picture, right? We we we, we were I was saying this is a binary. So um, the book goes on to oops, I went a little bit one two more. Um, then we go on to say that we need to assign distinct pulses, right? We need to assign a distinct pulse shape, right? And that's what those um, pulses were. Those are our distinct pulse shapes, and the possibility, and because it's binary, is either a 0 or a 1. No pulse represents a 0. A pulse represents a 1, right? And that's our binary pulses or our pulse code, right? For some of you who've already dealt with digital, this might be, oh, okay, duh. I've I already knew that. But when people are first developing and going through this process, these are all the things that they think about and consider to do. Okay, so if that was an obvious thing for you guys, sorry, but it's it's sort of the way these things are developed. Now going into, okay, so um, what happens, right, when we do quantization? What happens is, if you notice, you have already, right, this sample is kind of clear, you kind of injected a certain error, right? Because the sample would have been much higher than what you ended up with. So that error is what we call quantization error. And the error can be as much as plus or minus, right? Whatever the range for these levels are. And that range is what we call AV, right? Um, so the maximum quantization error is actually either plus or minus AV over 2, right? The quantization error always lies between those two, where AV is, right, you take the MP, which is the maximum or the peak value of your signal, excuse me, you divide it by 2 and you divide it by L and multiply by 2. And if you walk through it, you'll see that what we do is quantization error, I like to call it quantization noise. And you end up with a quantization error or quantization noise that is delta V, okay, squared divided by 12. Um, I think it's AV. Um, Looks like the equation editor did a little trick on me here. I am so sorry about that. Let me see if my pen lets me actually write it. The equation should have been, right. Let me see. Control P. Okay. The equation should have said something like, oh, AV square divided by 12. And you can see why the AV, my equation editor, I didn't catch this earlier, said delta V. But it's AV squared, okay, divided by 12. And because AV equals 2 the peak value divided by L, you can see how you can substitute that here, and you end up with an expression that says uh, your peak value squared divided by 3 number of levels squared. Okay, and that would be your quantization error. And why would we care about that? Because we are always interested in what our signal to noise ratio could be. Okay. Several advantages of doing all this digital stuff, right? There has to be a reason why we want to do this. Um, One of the really big reasons is digital communications, okay? Digital communication can withstand channel noise and distortion, something that you guys have studied, right? We've been studying in this course, much better than an analog signal, right? However, one of the greatest advantages that over an analog communication. So let's think about this, right? I have a transmitter. I want to go to this receiver, and let's say I want to go 100 miles, right? But let's say that, just as an example, that my signal, the way my system is set up, after 10 miles, the signal magnitude or power has lowered so much, and we did talk about Friis equation earlier in the course, right? The signal has dropped so much that I need to give it a boost, right? So I want to use a repeater. What a repeater does is takes your signal, applies something gain to it, hopefully conditions the signal and sends it along, right? Now, if we think about it from an analog, purely analog, what the analog system is going to do is going to do exactly what I just said. It takes the signal, um, it might filter it to get rid of any distortion, but any noise that the signal has picked up, any noise, any distortion that already fell in band, right, inside the bandwidth of the signal, right, um, you can't get rid of that, right? And when you amplify it, you're going to amplify the signal plus noise plus whatever distortion it has. And you send it on to the next repeater until you get to the final receiver. The difference with digital is at the same 10 miles, you can look at the signal and say, you know what, I'm going to regenerate the signal. What that means is I'm going to get the signal back to the digital bits that I originally sent. And with modern day technology, we can do this really quickly, right? Really fast. Even if it's voice or video, we can have these repeaters do this transformation real quick. And the receiver is none the smarter. They don't even know that we did that. Okay. Um, so this is a true advantage, right? Because you can recreate the digital signal again. An analog, once the signal is distorted, once the signal gets noise, it's going all the way to the receiver, and it's up to the receiver to see if it can get rid of it. And the problem with the analog signal, once the noise and the distortion gets what we call in band, it's too late. Okay. And the longer you go, the worse it gets, right? Because the more the signal uh, power is reduced, again, from what we know from Friis equation, thinking about wireless communication, right? Digital hardware in general is uh, just flexible, and we can use things like microprocessors, digital switching. Uh, they can be coded to yield extremely low error rates and high fidelity, like 4K videos and things like that. Uh, there are also digital signals are also easier to encrypt for security and privacy. It's a kind of hard thing to do with analog signals, even though you can. It is easier and more efficient to multiplex several digital signals. It's just putting the bits, and we're going to talk about this in a little bit more about multiplexing. Um, it's easier to exchange signal to noise ratio for bandwidth with digital signal. That's also true. And let's face it, the cost of digital hardware continues to drop, and it's approximately 2 or 3 years. It drops by half, while the capacity or performance actually doubles in the same period. So the cost comes down, and the performance goes up over time, right? Which is another advantage of digital. Okay. Now, if you want to know what the relationship, oh, we're doing all these things, and we can't forget we have only a certain bandwidth in our channel, right? We don't have infinite bandwidth, right? So when we assign a distinct group of n binary bits to the L quantization levels, right? That's what we do. Because a sequence of n binary digits can be arranged into the n distinct patterns, we know how to calculate L. And we actually saw this earlier in the course, right? This is L equals 2 to the n. Or if you want to know n, you have just do log 2 of L, right? Where n is the number of bits, right? Um, Now, because M of t, we're sort of restricting it to a bandwidth B, right? It will require at least a minimum of 2B samples. Again, that goes back to our Nyquist rate, right? So we require a total of 2NB bits per second, right? Um, so what that tells us is if we have um, a signal that we have sampled into N bits, right, we will need a minimum channel, B of t, right, hertz, that's equal to n, which is the number of bits, times the bandwidth of your information signal. Okay, so sure, going to digital requires more bandwidth. Okay, um, or does it? Right? There's more things that we're going to learn later on that we will be able to alleviate some of that. Okay, but in theory, this is the minimum transmission bandwidth required to transmit a PCM signal, right? A pulse coded modulated signal. Okay, so if you're just looking at the pulses, this is the bandwidth that you need. Okay, so I said we were going to talk some more about multiplexing, right? So you can take several lower bit rate signals and you can multiplex them or combine them and form what would be a higher bit rate signal, right? Um, Now, because in a multiplex situation, the medium is time shared by the various signals. This is what we call TDM, right? Time division multiplexing. Same thing, same deal, but this time we're in the digital domain, right? Ones and zeros. The signals from the various incoming channels, right, may come from many different sources. It doesn't really care, right? They're all digital. They're ones and zeros. Right. So some of them can just be voice, computer, telemetry data, faxes, even though not too many people use fax nowadays. And by the way, the different sources or tributaries, like the textbook likes to call it, do not have to be at the same bit rate either. Okay. In fact, what we're going to be doing is known as bit or digit interleaving. So we're going to interleave them, right? And there's again time division multiplexing. That's kind of what we started talking about. So you can think about it as this rotary switch, right? So you have this rotary switch. It gets a bit from A, then a bit from B, then C, D, and then goes all the way around. So A1, B1, C1, D1, then A2, B2, C2. And the receiver knows this and then knows how to decompose them, right? And so um, um, let me see. And this would be the case where they are all the same sort of bit rate. So we start off with a place where they're all the same bit rate and we just send them all. You can also do this at the word level. Remember when we were talking about the quantizer, the 16 levels, and we had 4 bits, we'll call that the 4 bits, or a byte, we can call that a byte, right? 4 bits, megabyte. You can actually do it at the byte level. So send a byte from A, another byte from B, then the byte from C, and the byte from D, right? There's different ways to do this multiplexing, right? So you multiplex them and you do it either at the bit level or at the word level. Um, Now, what happens when they're at different rates? You can still do the same thing, right? you can still have your multiplexer, right? It's just that now, for example, let's say you have the 4 channels, but this time A is going to have 3 times a faster rate. Well, that means you have to get a sample from A 3 times faster than from the rest. How does that happen? Well, A1, then you go to B1, then you have to come back to A because A is going to be ready. Then you go back to C. Then again, you're going to have to go back to A because A is going to be ready again. Then back to D. See, the rate is faster for A. That's what this figure is showing us here. Okay, so you have more samples of A than you have for the rest, etc. Now, um, we didn't mention that, but let me go back real quick. As soon as you start repeating, right before you start repeating, we call that a frame. So it's a frame of information. So a frame here is just 4 bits. A frame in the case that we're doing Word would be 16 bits because we have 4 channels, right? So it would be 16 bits. In this case, our frame is a little bit more complex, right? So our frame is till we get back to A4, right? So our frame here would be a total of 6 bits, right? So it changes our frame, right? We're multiplexing this frames a little bit different, right? And by the way, there's different ways to do this, right? You can have 2 switches that work at different rates and you can combine them. And again, this all happens in the digital domain. You probably never see it as a distinct signal anywhere because again, this all happens inside the digital chips. But it's good to know that this is what's happening, right? In order for digital multiplexing to work, at the receiving terminal, the incoming bits must be divided and distributed to the right place, to the right channel, right? Now, how in the world will the receiver know it starts getting bits, right? Um, so it needs to be able to have something to recognize, okay, here's where the data starts, right? So it has to be able to synchronize, right? So there has to be some kind of synchronization so that it knows when each frame begins, right? With so the way we do that, we actually um, do that by adding this framing or synchronization bits. So these are some extra bits that we put in, right, as part of our coding process, in addition to the data bits. Now these bits normally could have, let's say, a fixed pattern, right? It can be 1001, 110, whatever the pattern is, or however we decide to do that, right? It tells the receiver, okay, here comes another frame. Okay, here comes another frame. Remember, there's all kinds of things that happen between the receiver and the transmitter, especially when things are moving. And synchronization is becomes a challenge. It becomes the challenge or one of the challenges for the system, right? These extra bits that we're adding for synchronization, right, is what we call them overhead bits because they're not really part of our information, right, that we desire to transmit. They're there to help us synchronize things that we need to synchronize, right, and to be able to recuperate our information. So it's somewhat of an overhead that we had to add, right, to make things work. Um, Not all channels are active all the time, so some are transmitting data, some are idle. Um, what happens is in a case like this, your system, excuse me, is underutilized. Um, what that means is you can admit more input channels. Now, whoa, wait a second. Remember, we're talking about time, right? So what does a channel here mean, right? It really means a user. Think about it as meaning a user. So let's say I'm on a phone call and then somebody else wants to call, but I can take up to 10 different calls. So there's 8 time slots that are not being used, right? So that means more people can call in. Another 8 people can actually come in and continue to use the same channel, the same frequency channel, let's call it, right? Why? Because there's more time slots or time, if you want to call them time channels, but it really become time slots, right? There are occasions where nobody's talking, or maybe just one person, but the system can accept more, right? Up to it fills in our simple case here, the 10 time slots, right? Uh, so multiplex structures of this type, where um, you can sort of share the time, is what we call time division multiple access systems, right? They're not occupied all the time, and different people can occupy them. Actually, some of the modern systems, right? Okay, let's say they're allocating certain time to all 10 of them. Well, if not all 10 of them are there, and somebody's, let's say, is willing to pay a little bit extra, or maybe not even that, just the the cell phone companies, the provider wants to just have a happy customer, they might actually assign you the extra time slots. Right now, more of your data gets to go through. So if you're ever wondering how come I can't upload this as fast, whereas sometimes I can upload it faster, it's most likely one of the things. I'm not saying it's the only thing that can happen, is there's more people sharing the same um, resource, in this case, the channels. So therefore, you get less time slots. Okay. This is used all over the place, right? We mentioned satellite systems because they were probably one of the first people that to use this extensively. Telephony, cell phones everywhere is uses it a lot. Remember, you're not actually sending data all the time, but you're sending it fast enough and sharing these time slots that in speech and audio especially, you really can't tell the difference. Um, and video is even slower, right? Because our eyes can only go up to like 30 hertz. Anything that faster than that, our eyes can't really keep up with it. Right. Now, we talked about pulse coding. Let's go into this concept of differential pulse coding. And when I say differential here, I actually mean difference, like in subtraction, but not, don't think I'm just, uh, it's not like 5 minus 3 gives me 2, right? Let's talk about that a little bit and see what we mean. But the concept is sort of the difference between those two, okay? What happens with analog messages is you can always make a good estimate about a sample value, right? The next sample value, if you have knowledge of the past sample values. Another way of saying this is that the sample values that you're looking at, they're really not independent, and generally there's a great deal of redundancy, or another way of saying this is they depend on what happened before, right? Um, so we can actually exploit this redundancy and encode our signal with fewer bits, right? Fewer bits means more resources available. So if I can take and transmit the same amount of information with fewer bits, I really want to do that, okay? Um, so let's start off with a simple scheme here. Let's say we actually just transmit the difference between two different samples, right? So we are going to start off with just a simple subtraction. So I am going to say that instead of transmitting m of k, what I'm going to do, I'm going to transmit d of k, which is m of k minus it's the sample prior to it, right? So if k equals 2, d of 2 is going to equal m of 2 minus m of 1, right? So at the receiver, if you know d of k and the previous sample, m of k minus 1, you easily know what m of k is, right? You just take the difference, you add it to m of k, and you're done, right? Oh, isn't that simple enough? Doesn't seem like I'm saving much yet, right? Wait for it. Um, One of the advantages, there's several advantages to this, but one of the advantages is the difference is generally smaller than the actual sample values. Isn't that interesting, right? So think about a sinusoid, right? A sinusoid has a peak value of 1. Now let's say we're sampling it and let's say the prior value was 0.9. Now I would have, if I'm not doing differential encoding, I have to transmit the 10, the 1, the peak value of 1. Now if I do the difference, I only have to do 0.1, right? The difference between the peak value and the value before it, which I said was 0.9, so it will be 0.1, right? So therefore, the peak of what I'm transmitting is lower. That means I need less energy. Isn't that an advantage for us, right? Another advantage is because we're quantizing the signal, right? AV is MP, but we reduced our MP, right? The peak values. Now it's this difference. That means that AV, right, the quantized levels are going to be smaller, which in turn reduces the quantization interval. Therefore, it reduces the quantization noise. So not only do I need less energy, right, to transmit the same information, now I have less noise. Isn't that a benefit, right? So all this means is that given a number of n bits used for encoding, we can improve the signal to noise ratio, right, easily. Or for a given signal to noise ratio, we can reduce n, which is the number of bits, or the transmission bandwidth. Now we can do all these trades because we actually are using differential encoding. You can imagine the pleasant surprise of the people that first actually developed this, right? Now we can actually further improve this, right? So what if um, instead of just sending the difference, we had a better estimating or predicting scheme for the kth sample value, right? And instead of basing it just on the prior sample, we did it on several previous sample values. Now I'm going to stop right there. Now think about it. You're sending all these bits, and for some reason, your system has some impairment. It could have been momentarily, let's say lightning, and you lose one of your bits, right? Lightning happens really fast, right? And for some reason, that lightning caused you to lose a bit. Now, if you are doing regular encoding, the bit is lost, you lost the information, you probably have to retransmit it just to get it back, right? Or you start seeing all the pixelizations on your TV screen, for example. Uh, but if you had several of these samples, right, and they were grouped together, you would be able to say, oh, this group transmitted this group transmitted this, right? And you say, wait, these groups should have had certain level of correlation between them because some of the bits are the same. It looks like I lost one of these bits, and then you can start doing error correction at that point, right? And that's what this whole thing is about. So we're going to say that we have an estimate that we're going to call m hat, okay? So now d of k is actually our m of k minus m hat of k, where again, this is some kind of an estimate. Now, at the receiver, we also determine the same estimate. So we transmit an estimate, we determine the estimate, and lo and behold, by just adding the received DK to the estimate, you actually get your M of K back, right? And how in the world will we do this? Well, it gets complicated. It has to do with software and stuff. But you start having this receiver that is iterative, right? It's just sort of this loop thing. Anytime you hear something, something that's iterative, there's some kind of a loop. Somebody's making decisions for you, okay? So if your if your prediction is accurate, the predicted value of MK will be close to what MK has to be, and there will be a difference or prediction error will be even smaller than the difference between the successive samples, right? And this is what we know as differential post-coded modulation or DPCM. And it's superior than the simple one-step prediction that we were talking about just a second ago. I'm not going to go into all the details. The textbook does. So you guys have a reading assignment. So please go look at sections 5.1 and 5.5.1 and 5.5.2. But just a little bit of a high level, if you guys will allow me. Let's say here's our information signal. Let's not talk about this part at first. We're going to have some DFK. This DFK is going to be quantized. So we're going to end up with the Q of K. Now this dq of k is going to come in here into the summation, which is going to be with our, what do we call it, our estimate of samples, and it's going to be added to that. And that's what's going to produce our quantized MQ of k. This is what, at the end of the day, the receiver has to recuperate. It's not M of k because we quantized, right? And if we weren't doing this differential post-coding, M of k would have gone to the quantizer. Instead, we did this difference. Now, this summation is going to go into the predictor. This is the one that's doing all that computation and that stuff with the prior samples and stuff. And that's the one that produced the M hat quantized. That gets added to M of k to produce, subtracted from M of k, excuse me. See, there's a minus sign here. So whenever you see a summation symbol like this and there's a minus somewhere, that means this minus this. And that produces the k. So now you notice that what we send down the channel is the differential d of q, which has the predictor information in it, right? Now on the receive side, you're going to have the differential difference quantized. It's going to come into the summation, right? And before it goes to the output, right, you're actually going to have the predictor that works very similar to this one, right? But this one produces, again, m hat of k, which is the same one as this one, or should be. But notice there's no negative sign now. So before we were subtracting that from d of q, the m of k, but here we're actually going to add it to m of q. M hat plus d of q actually produces m of q of k, which is this guy, the one that we said we wanted, right? And notice that this mq of k is actually m of k quantized, right? Which we know we can recuperate, right? We'll have to do some interpolation and some filtering and all that stuff to get our signal back, but this is the process, right? Again, read the book. The book does a nice way, nice detailed way of explaining it. Um, do look at the math, but don't get too wrapped up in it, okay? All right. So why is it that I said that there's some signal to noise improvement from that, right? Can we quantify it? And the answer is yes. So, and we're going to talk about signal to noise improvement. And this is one of those things that in the field of practice, some people might call this a process gain or a processing gain. And it is, right? It's the fact that you're using differential PCM, a DPCM, and it produces a certain processing gain because we're using a group of samples and we're using this prediction, and that gives us uh, an improvement to our signal to noise ratio, which at the end of the day looks like a regular gain, like a gain from an amplifier. So if we use the values of L, right, for both cases, both differential and non-differential, the quantization step A of B and the PM is reduced by the factor dP divided by MP, right? Because we know what the quantization noise is, right? And we know what the reduction factor is. We know that there's an increase in the signal to noise ratio, right? By this same factor. Um, we also know that power is proportional to the peak of the signals. We've seen that all throughout the course, and you guys seen this actually elsewhere. And as long as no other properties are changing, none of the statistical properties of your channel, your signals, everything else stays the same, we can talk about this G of P, right? This gain factor, which is our signal to noise improvement. And again, I'm going to call it processing gain. And G of P is nothing but the power of M divided by the power of D, right? Um, where PM and PD are the powers of M of T and D of T respectively. And again, if you have a certain signal to noise ratio, and I tell you that the signal to noise ratio improvement for using DPCM is so many dBs, right? Signal to noise ratio in dBs, the improvement is dB. You just add them together because they're both dBs, right? We studied that early on in the course. Okay, which is hopefully by now you guys see why I insisted so much on the dB stuff at the beginning of the course. All right, so that's it for our lecture today. Thank you so much, and I'll see you in a future lecture.